Controlled environment, plant production, engineering, technology, education modules are developed and presented by The Ohio State University, Rutgers, the State University of New Jersey, and the University of Arizona, with support from USDA, NEFA, through their Higher Education Challenge Grant Program. This module is the Basics of Greenhouse Environmental Physics, Part 2. This module is presented by Dr. Murat Kasira of the University of Arizona, Dr. A.J. Boat of Rutgers, and Dr. Cherry Kubota of the University of Arizona. The state of important greenhouse variables is determined by energy and mass balances. In this section, the various terms of energy balance will be discussed. When considering an energy balance in a greenhouse, it is important to divide the greenhouse into individual components, which may be considered separately. These components include the greenhouse cover, the greenhouse air, the crop canopy, and the ground. The primary source of energy for greenhouse is solar radiation. Total solar radiation can be divided into direct and diffuse radiation that transmits through the cover, is absorbed or can be absorbed by the cover, or it's reflected by the cover. There are other exchange processes happen between the greenhouse interior and the exterior, and also between greenhouse interior and the crop canopy to ground, or greenhouse interior to ground. As you can see in this image, some of these exchange processes are illustrated. For example, the conduction, the convection, heating and cooling, evapotranspiration from the plant canopies, conduction between greenhouse interior and to the ground, as well as greenhouse ventilation or infiltration from or to the greenhouse space. Let's look at this graph now to examine the spectral irradiance based on the wavelength for solar radiation. The majority of solar radiation is within the wavelength of 300 nanometers to 2500 nanometers. The range between 380 and 770 nanometers is the visible light. The range between 400 nanometer to 700 nanometer is called photosynthetic active radiation, or represented by PAR, which is specific interest for plant growth. A small portion of this radiation is used for photosynthesis, while the rest is converted to heat. The interactions of solar radiation within the greenhouse glazing determine how much energy enters the greenhouse system. Let's now look at the thermal radiation exchange process. In regards to thermal exchange between the greenhouse interior and the atmosphere, this can be determined by evaluating the radiation exchange based on the temperature of the greenhouse exterior and the sky temperatures. Radiation exchange with the sky is a complex phenomenon, as the emissivity of the sky and sky temperature are both difficult to determine. However, if one considers the emissivity to be unity and measures actual net outgoing radiation, an apparent sky temperature can be determined. When it is raining, for instance, or completely overcast with fog or low clouds, the effective sky temperature is the outside ambient temperature. The clearer the sky, the lower the effective sky temperature. When the sky is very clear, as on a crisp, clear winter night, the heat loss by radiation is maximum. Now let's look at greenhouse ventilation and talk about natural ventilation process. Since the greenhouse covering prevents the internal air to be mixed with the external air, ventilation is necessary to transport energy and mass into and out of the greenhouse. Ventilation natural ventilation is either driven by differences in pressure between the inside and outside of the greenhouse, called wind effect, or differences in air density between the inside and outside of the greenhouse due to temperature differences, called the stack effect or the buoyancy effect. These are the two main driving forces for greenhouse natural ventilation. In the case of natural ventilation, pressure differences are caused by outside wind. Now let's look at water vapor balance. In the case of water vapor, the following components are of interest for us: crop transpiration, condensation, and ventilation. Water has a huge bearing on environmental conditions inside a greenhouse, which makes the water vapor balance an important consideration. Water heating and evaporation require a relatively high amount of energy that is taken from the surroundings within the greenhouse, making its presence within the greenhouse necessary to quantify and analyze. Let's now look at some of the humidity terminology used in greenhouse energy balance analyses. The three ways to quantify the water vapor content in air are absolute humidity, which can be represented by the kilograms of water per volume of air, and specific humidity, that is the mass of vapor per unit mass of air, represented by kilograms of water by kilograms of dry air, and finally in terms of partial pressure or vapor pressure with pressure units. Since the amount of water vapor in the air is relatively small at ambient air temperatures, we can assume that the air is an ideal gas. Therefore, it is possible to relate both specific and absolute humidity to partial pressure. Assuming ideal gas here for the air also helps us to use conversion of units among these three definitions, which can be done by multiplying factors that are almost constant and that the three definitions are equivalent. I'd like to mention also that the maximum or saturating amount of water vapor that can be contained in a portion of air also depends heavily on the temperature of the air. I like to mention here that the maximum or saturating amount of water vapor that can be contained in a portion of air depends heavily on the temperature of the air. The vapor pressure is exponentially increased as the temperature of the air is increased. Other quite common definitions of air humidity take this factor into account. For instance, relative humidity, which is the ratio of vapor pressure to saturation vapor pressure, and vapor pressure deficit, which is the difference between saturation vapor pressure and vapor pressure of the air. These two definitions of air humidity takes the relationship between air vapor pressure and temperature into account, and they're commonly used as the humidity terminology when it comes to greenhouse energy balance. Relative humidity and vapor pressure deficit quantify the drying power of air, which is the amount of vapor that air at any given temperature is able to absorb. In addition to these terminologies, we can also define dew point as one of the humidity terminology, and dew point is also a measure of humidity, which is the temperature at which a given vapor content would be saturating. Let's look at the water vapor balance of the greenhouse system. We can define the water vapor balance in the greenhouse system with this equation. Some of the terms in this equation are the V, the greenhouse volume, and greenhouse ground area ratio with this term, and the change of water vapor content of the air in time, and this left hand side term equals to the right hand side term, where we have the crop transpiration minus the water vapor flux due to condensation from the surface of the cover, as well as minus the water vapor flux due to ventilation and leakage to the outside of the greenhouse. Now let's discuss about the energy balance of a wet surface. In order for water to evaporate from a surface, we need energy for evaporation. Furthermore, the air that is directly in contact with the surface needs to be removed so as to replace it with unsaturated air that can absorb water. For a wet surface exposed to solar radiation, the absorbed energy given by solar radiation will need to be converted to sensible heat and latent heat components. The latent heat is the energy absorbed by or released from a substance during a phase change from a gas to a liquid phase or a solid, or vice versa. And the sensible heat is the energy required to change the temperature of a substance, but in this case with no phase change. So therefore, for a wet surface exposed to solar radiation, a simple energy balance on a surface can be performed assuming steady state conditions, so the input minus output equals to 0, and we can write the energy balance as the net radiation exposed to the surface minus the sensible heat component and minus the latent heat, the evaporation component, and that equals to 0. We can evaluate the evaporation term that appeared in the water vapor balance of the wet surface that we described in the previous slide. And in this case, we can use Dalton's diffusion equation here, as you can see. And the rate of evaporation is dependent on the concentration gradient, similar to conduction, and can be written in this form. In this equation, the Gb defines the conductance, which is a mass transfer coefficient, and that can also be defined as the inverse of the resistance, which is Rb, as we can see on this equation here. Writing the previous equation in terms of this equation, in terms of partial pressure and including resistant terms, then the evaporation equation takes this new form, which is also a function of temperature. To find the evaporation energy, the rate of evaporation can be multiplied by the latent heat of water, as you can see here with the lambda term, which helps us to find the evaporation energy. And here you can see some of the terms or variables involved in calculation of evaporation from wet surfaces, which is our discussion in this slide for the latent heat portion of the water vapor flux balance from wet surfaces. The sensible heat component of the water vapor balance from wet surfaces can be calculated using the following equation, as you can see here, which is also dependent on the temperature difference between the surface and the surrounding air. The other variables involved in this analysis are the specific heat of the air, represented by Cp, air density, and also the resistance against the water evaporation or diffusion into the air. Now we can summarize our discussions on water vapor balance from wet surfaces. Again, let's remember our schematics to include radiation incident on the surface and the sensible heat from the surface, as well as the latent heat from the surface. So our energy balance at steady state was the radiation minus the sensible heat minus evaporation component, and that equals to 0. And we can solve this equation for net radiation on the surface. Finally, introducing our terms for individual exchanges for sensible heat component, as you can see here, as well as the latent heat component with this equation, part of the equation in the balance. We can have a further detailed equation for the energy balance of the wet surface for the water vapor balance. Now we can see in this equation that there are sensible heat and latent heat components involved, as well as net radiation on the surface. We can use the same approach and relate these energy exchanges on a leaf surface to determine evapotranspiration, both evaporation and transpiration from a leaf surface. Our equation in this case for evapotranspiration looks very similar to the water vapor balance of a wet surface. Now we introduce some new terms here in this equation for the evapotranspiration calculation, and one of them is the leaf area index, which is a unitless term, and that is the ratio of total amount of leaf area divided by the ground area for the plant canopy, as well as the aerodynamic resistance introduced into the sensible heat term. Instead of the resistance term here you can see for the wet surface water vapor balance. Another resistance term that we introduce to the latent heat component is the stomatal resistance, which is the resistance against the water diffusion from the leaf stomate into the surrounding air. Let's remember our equation again from the previous slide for the water vapor balance on the or energy balance of the leaf surface, and the related components for this analysis on the leaf surface: the solar radiation component, the sensible heat, and the latent heat component. Our final equation for the energy balance on the leaf surface is summarized in this equation, with the solar energy term on the left hand side, that is the available energy for the plant, and on the right hand side we have the sensible heat from the plant with related variables, for instance the temperature difference between the leaf surface and the surrounding air, leaf area index, the specific heat of the air and the density of air, as well as the aerodynamic resistance term against the sensible heat, as well as the latent heat component, where we have the surface specific humidity and air specific humidity difference, as well as the aerodynamic and stomatal resistance component, leaf area index, the density of the air, and the latent heat of water. And this energy balance is actually the well-known Penman-Monteith model for the energy balance on leaf surfaces. With the following equation, we can determine the water vapor flux condensing from the greenhouse cover, considering the mass transfer conductance as well as the specific humidity difference between the cover surface as well as the surrounding air. Water vapor balance in the greenhouse energy balance analysis should also consider the water vapor flux due to ventilation, and in this analysis we can consider the ratio of greenhouse volume to greenhouse area, as well as the air exchange rate and the absolute humidity difference between the greenhouse interior and the outside air. So far in our presentation, we discussed about the energy and mass flows to and from the greenhouse system and how they affect air temperature or water vapor concentration in the greenhouse environment. Then we discussed about how such energy and mass flows can be quantified. When we consider energy and mass balance for the greenhouse system, we need to consider the law of conservation for any given volume. In this case, the greenhouse was our control volume. In order to establish a general rule, we first considered energy, then we easily convert that into discussions for the mass flows and mass balances. Now let's talk about the exchange processes, energy exchange processes in greenhouse environment. Let's consider that we have a greenhouse as our control volume and a crop canopy. When the outside temperature is higher than the greenhouse air temperature, the energy gain of the greenhouse will be determined by the solar radiation availability and energy input to the greenhouse system due to convection process and due to conduction process through the walls, as well as energy gains due to ventilation process. Some of the energy losses will include radiation to the sky, as well as energy losses to the ground due to conduction. The system will also be affected by the greenhouse cooling process and the energy related to that, as well as the eruptive cooling of the crop evapotranspiration. So in this case, when we observe higher outside temperatures than greenhouse air temperature, at steady state, we can write an energy balance for the greenhouse system, including all the energy gains of the system and energy losses of the system. Similarly, when we observe lower outside temperatures, when the greenhouse air temperature is higher, then we consider solar radiation as the energy gain for the greenhouse system, as well as the energy gain of the system due to heating process. And the heat losses will include the convective heat loss, radiation loss to the sky, and energy loss due to ventilation, energy loss to the ground due to conduction process, as well as the conduction through the wall, as well as the energy exchange between the crop canopy and the greenhouse interior due to the evapotranspiration process. So when the outside air temperature is lower at steady state, we can redefine our greenhouse energy balance, as you can see with this equation, considering all the energy gains as well as the energy losses from the greenhouse system. You can find further details of our discussions in this module using these references: Greenhouse Climate Control and Integrated Approach, Greenhouse Technology and Management, and Greenhouses, Advanced Technology for Protected Horticulture. We would like to acknowledge the funding received for our effort by the USDA NIFA program.